Okay, yeah, let's get started. This week's lecture is on proximal policy optimization. So we're really pushing sort of frontier methods now. Proximal policy optimization is one of the most popular methods used in practice. It tends to be very stable and not require too much tuning. And the first generation of large language models was trained using proximal policy optimization for the reinforcement learning part of it. So it's a very popular method, and we're going to go through it today. Okay, first let's recap what we covered last week. So last week was on advantage actor critic, A2C, and a bunch of sort of derivative methods and associated methods. So we started by talking about behavioral cloning. And if we'll recall, the way behavioral cloning works is we assume access to a data set of optimal behavior or very good behavior, so expert level behavior, and then we just train to fit to all of those actions. And this is behavioral cloning. Then we covered reinforce. So behavioral cloning doesn't require a reward signal, it just requires that we take good actions. Reinforce allows us to use mediocre actions and a reward signal to learn what to fit to. And the way we do this is we fit more strongly to actions that lead to a higher return. And this leads to better behavior. So reinforce has the same basic objective as behavioral cloning, except we weight all of the actions via their return, and then we preferentially fit to actions that have a higher return. This is how reinforce works. We saw that reinforce is not just an arbitrary scheme cooked up from nowhere, but instead is justified by the fact that, by the policy gradient theorem. So the policy gradient theorem tells us that doing reinforce updates is exactly equivalent to doing approximate, because you're sampling, approximate gradient ascent on the expected return. And because the expected return is the thing we ultimately care about, this is in some sense, the right thing to do. You're just doing gradient ascent on the thing that you actually care about increasing. Then we covered reinforce with baseline. What this does is that the returns are now normalized by taking away their value of the state that they were obtained in. And what this does is this changes our weights so that our weights are now, are you doing better or worse than expected? So if the return is higher than the value of the state, this is better than expected and you should fit to this action. If the return is worse than the value of the state, you're doing worse than expected and you should unfit from the action. You should decrease the probability of that action. And we sort of generalized reinforce with baseline to this more general framework of advantage actor critic, where just like reinforce with baseline, we have weights, which are advantages associated with each action, and we preferentially fit to those actions that have positive advantages and unfit from those that have negative advantages. And the advantage here is interpreted as how much better is this action than the baseline, than the state that you're in. So how much does the value of the action improve over the value of the state? So we covered all of these, and we're going to see some recurrent themes here coming up in PPO, and we're going to try to sort of understand PPO as an improvement over advantage actor critic, so as an advance over this general method. So this week, the first thing we're going to do is cover network architectures for policy gradient methods. So last week we covered policy gradient methods, but we didn't talk a lot about like how you'd actually implement these and what the networks that you used for doing these methods, what those networks would actually look like. And that's what we're going to cover this week. We're going to cover the relative policy performance identity, which is sort of the theoretical underpinning of PPO. The theoretical underpinning of last week's lecture was the stochastic policy gradient theorem. The underpinning of the theoretical underpinning of this week's lecture is the relative policy performance identity. We're going to discuss something called the surrogate advantage, and then we're going to discuss how to optimize the surrogate advantage, which we're going to understand PPO as doing. And finally, we're going to discuss the specific way in which PPO does this, the specific way in which it optimizes the surrogate advantage. Okay, great. Let's get started. So first things first, we'll talk about network architectures for policy gradient methods. So if you have a discrete action space, then your policy is going to output probabilities of each action at each state, right? So the state's going to be fed into the network. And remember, states here could be frames of an Atari game. They could be representations of all the joints of a robot or a 3D animal thing that you want to move about, anything you like. So the state is going to be fed into the network. And what the state is determines the sort of base of the architecture of the network. So if it's language, you're probably going to be using a transformer. If it's Atari frames, you're probably using a convolutional network. Other things, you would probably use an MLP, but you're going to feed your state into the neural network body. And this neural network body can have any architecture you like, provided it's sensible for the task at hand, sensible for the type of states that you're feeding it. Then the network is going to compute logits associated for each action. So this is just like the action values. We're going to have one logit for each action. So here there are 6 actions, and we're going to have a linear readout going to each one of these actions, or corresponding to each one of these actions, generating logits. And as was pointed out last time, you don't necessarily need to have like 6 separate heads. You can just have one head that maps to a 6-dimensional space, where each dimension of that space corresponds to one of these logits. So the point is that you have a linear map of some kind that maps into logit space. Then, so the logits, because you're getting them from a linear map, they represent how plausible each action is, but they don't have the properties of a probability distribution. So probability distributions have 2 very important properties. They are all positive, right? You can't have a negative probability, or all non-negative, I should say. And they sum to 1, right? So I can't have probabilities that sum to 2 or 0.5. I can't have any of them being negative. So what I need to do is I take my logits and I need to apply an operation to them that's going to make them all positive and then normalize them so they sum to 1. So this operation is called the softmax, and we're going to apply it here. And after applying the softmax to the logits, we get probabilities for each action, right? And the way the softmax operation works is that for each logit, I do e to the power of that logit, and then I divide by the sum of e to the power of all the logits. And we can interpret this in 2 steps. The first one is enforcing non-negativity. So e to the power of anything will always be positive. And so this part here enforces that the probability of each action is non-negative. And then the second part, underneath the fraction, is going to normalize this sum to 1 by just dividing by the previous sum. All right? So the softmax operation is a way to go from logits, which are unnormalized and can be negative, to a probability distribution, which is normalized and everywhere positive. Does anyone have any questions about this before we move on? Great. So this is how you would build your network architecture if you had a discrete action space. What about a continuous action space? So what if I'm controlling the joints of a robot and I have a continuous amount of torque I can apply on every single one of these joints? So in this case, I can't just directly output a probability for each action. I have to do something else. So again, I'm going to feed a state into the network. And again, this neural network body will be something that is appropriate for the task at hand. And then this network is going to then output from usually a linear map at the last layer, possibly with some other nonlinearities on top, distribution parameters for a distribution over actions. So the network is now mapping from states to distribution parameters. So by distribution parameters, I mean, so what are some frequent probability distributions? One of them is a normal, right? Normal distribution is a frequently used probability distribution. Normals are parameterized by a mean and a variance. And so my neural network would map to a mean and a variance, because these are parameters that define a distribution. Other popular distributions, a beta distribution. A beta distribution has 2 parameters, has an alpha and a beta, and those are the things that my neural network is going to output, right? So any distribution that lives within a parametric family is defined according to some set of parameters, and your neural network can just map to this space of parameters and output parameters for that distribution. So let's go through a concrete example of a multidimensional Gaussian, right? So what defines a multidimensional Gaussian? So imagine that our action space is d-dimensional. So we have d dimensions of the action. So these could correspond to d different joints at which we can apply a torque, for example, right? So if our action space is d-dimensional, we need to output the parameters of a d-dimensional multidimensional Gaussian. So what defines a multidimensional Gaussian? Well, a multidimensional Gaussian is defined by its mean and its covariance. So our neural network is going to take in states, apply some processing, and then at the very end output the mean and covariance of this Gaussian distribution. And then the probability of any action given a state and our network parameters is just going to be a normal evaluated at that action with that mean and that covariance. Right? So this is the exact formula. It's not super important as long as you know how a multidimensional Gaussian works. Right? And this general principle can be generalized to any distribution you like that's parametric, that you map from your input states, you do some processing, and then you output parameters for that parametric distribution. And then you have probabilities for each different action defined according to that parametric distribution. All right, any questions about this?
Is this the state-of-the-art way to deal with continuous action spaces like this? I didn't know it was so probabilistic.
Yeah, so the question was, is this the usual way to deal with continuous action spaces? And the answer is, yeah, in any method that's policy gradient. Well, okay, so in methods that are stochastic policy gradient, yes. So DDPG and TD3, DDPG we covered in, I think, the third lecture, uses a deterministic policy. And in this case, you just have a direct map from states into actions. But provided you're learning a stochastic policy, this is the typical way that you would do it. Yeah.
And do you still train this network in a usual fashion? You're just optimizing over parameters, so you don't need to actually make the computations probabilistic in some sense, like make it Bayesian or something.
Yeah. So the question was, given that you're like using a probability distribution here, do you need to make any of the like computations stochastic or probabilistic or Bayesian? And the answer is no. You don't really need to do anything special. You just need to like be able to compute probabilities for each action, right? And that's all that this does. It gives you a way of computing the probability of each action and a way of sampling actions from any given state. So you feed in a state, you get a mean and a covariance. This defines a distribution, and then you can sample actions from that distribution. This gives you a way from sampling from your policy at every single state. Yep.
So is there a fundamental benefit of stochastic policy? Why would usually we work out for the most of it?
Yeah, so the question was, is there a benefit to having a stochastic policy? And the answer is typically that this allows for exploration in the environment. So if you are sampling from a distribution over actions, then you can explore different actions and gradually like narrow this distribution down over time. So this is one reason why stochastic policies are popular. Also, if your environment is partially observed, so you don't have full information, there are environments for which the optimal policy is in fact stochastic. It's only when the environment is fully observed that the optimal policy is going to be deterministic. So you can construct some like fairly simple toy examples where you're only partially observed, or your features don't uniquely describe the state, and in this case, stochastic policies can be optimal. Yeah. Yeah.
So your output of this network is going to be, is it strictly parameters, or do people maybe like output moments, or like,
yeah. So the question was, is it always parameters? Is it sometimes moments? It's not always parameters. This is the most common way to do things, but there are other like fancier things that you can in fact do instead of defining it via the parameters of a distribution. So soft Q learning, for example, does this like very fancy trick where they essentially have a network that transforms noise samples into actions, and then they use a technique called Stein variational gradient descent to work out how to update those network parameters. But this is like quite fancy, and it's quite normal to do this. This is sort of the most standard way. And if you're outputting instead like moments of a distribution, then provided you can map from those moments to the distribution, you're just secretly outputting outputting distribution parameters. Right? You're just parameterizing the distribution in a different way. Yeah. Any more questions before we move on?
How do you train this sort of thing? So what type of loss are you using if you're outputting parameters, and like how do you train it? Like what?
Yeah. So the question was, how would you train this? And the way you train it is just by using this explicit this explicit version of the distribution, right? So this gives you a formula that tells you the likelihood of any action given any state and set of parameters, right? That's what you have here. And then in both all of the methods we saw last week, so all of the policy gradient methods or behavioral cloning, you have a log probability term, and you want to take the gradient of this with respect to theta. And so all I do is I take this expression here, I take the log of it, this just gives me a function that's a function of theta, and then I just differentiate back through that. Right? Yeah.
Do you differentiate with the specific action taken or by averaging the cost of action?
Usually the specific action taken. There are some situations where you would like average over actions, but usually the specific action taken. Yeah.
Even the specific action taken, the gradient is well defined.
Yeah, so you have your trajectory. On this trajectory are various state action pairs, ST, AT. You take ST, AT and plug them in here, and then this is just a function of theta then, right? Once you've fixed AT and ST, you just have a big function of theta, and if you've got a function of theta, you can backprop through it. Yeah.
I remember last time we looked at a case where you want to optimize the action value function with respect to action, but I can't remember the exact context of it.
Yeah, so in DDPG, you're optimizing the action value function with respect to the policy, yeah.
Yeah, so is it possible to have this network here output a score, like a gradient of the log of pi, as opposed to the likelihood of the action itself, which would give you a shortcut to, differentiating gradients?
So the question was, could you instead output the score function, so the grad log pi instead of pi directly? You could do this, and it's not like a terrible idea, but you also need to be able to sample from this really efficiently, right? And if you're computing a score, then your sampling is probably going to be like less efficient. But there are methods that use like diffusion to sample actions instead. So there are like a whole cornucopia of like other ways that you can define a stochastic policy. This is just the most common and sort of default one.
Yeah. This is why I brought up the optimizing over A previously, because if you're taking gradient steps over A anyway, then
yeah, so
you have it within your computational task to optimize over A.
If you're in a stochastic setting, you're typically not taking gradients with respect to A. So in the deterministic setting, you are, so DDPG in particular, you are doing gradient steps with respect to the actions. But in a stochastic setting, you're typically not doing this. This is like kind of a weird thing to do, and it doesn't happen very often. So yeah, you're instead you're taking gradients of probabilities, and provided you can express your probability like this, once you fix an action and fix a state, so you fix action AT and state ST, then this is just a function of M and C, right? And so tacitly a function of the network parameters, and then you just backprop through those network parameters, and you're all good, right? Great, okay. So typically, if you're using a multidimensional Gaussian, you take the covariance to be diagonal. And this simplifies things massively because the number of parameters you have to output is quite small. You have, for each action dimension, you have one mean variable and one variance variable, and so you're just outputting 2D variables that define your distribution.
So instead the trouble of inverting a matrix and
yeah, you also don't need to compute this determinant and don't need to invert the matrix. So this is, yeah. Okay, wonderful. So now we're going to cover the theoretical basis of PPO, which is the relative policy performance identity. Okay, so we're going to recap the policy objective. So last week we covered reinforce with baseline, and advantage actor critic. And we also saw that reinforce with baseline is just secretly a particular choice of advantage actor critic. And all of these methods are different ways of performing gradient ascent on the policy objective. By the policy objective, I just mean the expected return when I sample trajectories according to my policy, right? So the policy objective, curly J, calligraphic J here, which I'm going to use throughout, is just the expected return, so the expected sum of all the rewards along my trajectory when I sample trajectories according to my policy, right? And these methods all they do is give you a way of estimating the gradient of this thing. Yeah, so the policy objective is the cumulative reward obtained by the policy. Okay, any questions before we move on? Great, all right. Let's recap a second core concept, which is the advantage function. So the advantage function specifies how good the value of an action, so how good an action is relative to the state that you're in. So if you're in a really good state and you perform an action that just gets you a kind of pretty good reward, you haven't actually done a good job. You've done a bad job because you've blown it. You were in a really good state, you could have done really well, and instead you just did okay, and so you have a negative advantage there. But if you're in a really bad state and you end up doing fine, then this is a positive advantage. You've done better than expected. So it's about, is the action better than the average value of the actions or the value of the state, right? And so this is how we define the advantage function. The advantage function of a state-action pair is just the value of the state-action pair, the action-state-action is the value of that state-action pair minus the value of the state, right? So it's relative value of an action. And advantage actor critic uses advantage estimates formed using sample rewards and approximate value functions. And we covered that there are many ways that you can form these advantage estimates, and some of them have better properties than others, and there are reasons why you might want to use one in one context and one in another. And everything that I said there also holds for today. So we're also going to be forming advantage estimates. And again, there are many ways to do this. And all of them can be used in PPO. Yeah, any question about this before we move on? Cool. Okay. So, what does the relative policy performance identity say? So, given our current policy parameters, so we have a current set of policy parameters, which I'm going to call throughout theta old. This is the current set that we have, and we want to find new parameters that improve upon them. Okay? And then the idea is going to be we're going to just keep obtaining new parameters that improve upon our old parameters. So one way to do this is to maximize policy improvement, which is just the difference of the policy objectives. So I want to increase, I want my policy objective to be higher my new set of parameters than it was for the old set of parameters. So this is the policy improvement. Yeah, any questions? Yeah?
Sorry, I missed last session. What is J? What is this notation?
So J is this. So the expected return under trajectory sample for my policy. Right? So it's the thing that we actually care about. It's the thing that we really actually want to maximize. Great, so we want to maximize this policy improvement of what's the value of our new policy relative to the value of the old policy. Right? And notice that maximizing this is just equivalent to maximizing J theta nu, but seeing things in this light is going to be useful for us later. So the relative policy performance identity tells us that the policy improvement, which remember is just J theta nu minus J theta old, can be written as the expected, so let's break this down. So this is the policy improvement, J theta nu minus J theta old. What's going on here? So I'm taking an expectation, and the expectation is with respect to trajectories that are sampled according to my new policy, right? So if I sample a bunch of trajectories according to my new policy, and then that's the expectation that I'm taking here, trajectories under my new policy. And then what am I taking the expectation of? I'm summing over time steps on the policy. So I'm summing over, time steps in the trajectory. So I'm sampling trajectories according to my new policy, summing over time steps on those trajectories of the advantage of the state action pairs under my old policy, right? So if my old policy has an advantage function, that's this, and then I'm sampling state action pairs according to my new policy and computing their average advantage. Okay, this is like a lot going on here. So any questions before we move on? Cool. Okay. So the interpretation of this is that the improvement in a policy, the improvement is the sum of the advantages of the actions taken by the new policy evaluated according to the advantage function of the old policy, right? This kind of makes sense, I think. When you look at these two things, you can sort of imagine how they would come out to be the same. So here I'm asking how much better does J nu do compared to, how much better does theta nu do compared to theta old? And the way I'm answering that is, well, if I sample actions according to theta nu, then how much better are they than baseline, which is what the advantage function tells me, when compared to the baseline of theta old. And then I'm just summing this over all time steps because I'm looking at a holistic measure for the entire trajectory. So like maybe you can imagine how this derivation goes. We're not going to derive it here, but you can look it up. It's not super complicated.
Can you give some intuition why it's not inverted? Why it's not acting according to the old policy and then benefiting, taking advantage according to the new policy? That's what I guess.
Yeah, so the question was, what's the intuition for why it's this way around, why you sample according to new and evaluate according to old? I think it's because you're imagining that at each state, you're asking like how much do I improve upon my baseline, right? So interpreting theta old, so when it's written this way around, j theta nu minus j theta old, the way to interpret j theta old is as like a baseline that I'm measuring my performance relative to. And then this also comes into the advantages, right? Where my advantage function basically asks how much better is an action that was sampled relative to a baseline where my baseline is defined according to theta old. So I think this is the intuition, that because theta old acts as the baseline, it makes sense that it defines the advantages. Yeah. Any other questions about this? Cool. Okay, let's move on. So the relative policy performance identity tells us this, as I'm just writing it back up again. Okay. So last week we learned how to form advantage estimates. So we know, given a state action pair, we've learned multiple ways that we can form advantage estimates for that state action pair. So this is good, right? We have advantages appearing here according to the old policy, and we know how to form those kinds of advantage estimates. So that's a good starting point. But computing this requires us to take an expectation over trajectories according to all potential new policies, right? So if I actually wanted to use this, like what's the most obvious way to use this? Well, I could sample a bunch of theta nus that are close to my theta olds, perform a bunch of rollouts using them, and then compute all of these and do a comparison. But this is like very, very computationally costly because I would have to sample a lot of trajectories according to a new policy. So in essence, the problem here, another way of rephrasing this, is I'm trying to use this to find a good theta nu, right? But in order to actually use this expression, I have to already know what the theta nu is, because I need to be able to sample trajectories according to that theta nu, right? So I don't know what the theta nu is. If I don't know what this new parameter I'm trying to get is, then there's no way for me to sample trajectories according to it. And if I can't sample trajectories according to it, I can't evaluate how much better it is. And so the whole endeavor is kind of doomed, right? So the good thing is we have advantages and we know how to deal with them. And there are advantages according to the old policy. So we know how to form those kinds of advantages. The downside is we need trajectories according to a new policy, and we can't generate these, right? And this is going to lead us to develop the surrogate advantage as a way of dealing with this problem. So we're going to start with the relative policy performance, so this thing that we've been dealing with for the last few slides. And we're going to decompose this trajectory, this expectation over trajectories, right? So this expectation over trajectories, we can consider this as comprising two separate things. One is an expectation over action choices, right? So at any given state, this distribution over trajectories has a distribution over actions from that state. And the reason there's a tick here is because if I have my new network parameters, it's very easy to sample actions or to evaluate the probability of actions at a new state, right? So at any state that I like, right? So at any state that I like, it's very easy for me to sample a bunch of actions at that state. So this is good. The expectation over action choices, that's not a problem. What is a problem is the expectation over states, right? So I have an expectation here, and I'm plugging in all STs for all the time course of my trajectory. And those states that I visit are from a rollout according to this new policy. And it's in general pretty hard to evaluate what the probability of visiting a state is going to be under my new policy without just doing a collection of rollouts, right? So of this expectation over trajectories, we can decompose it into an expectation over actions and an expectation over states. And the problem term is the expectation over states. Anyone have questions about this? Cool. Okay. So what does this suggest that we do? Well, maybe we can come up with an approximation where we don't have to deal with this expectation over states. So the key idea of surrogate advantage is that if the new policy is close to the old policy, then the states that you visit will be similar. And so we're going to approximate this relative policy performance. We're going to approximate that by replacing the expectation over states with respect to theta new with the expectation over states with respect to theta old. And so this only requires that I have a sample of states rolled out from the current policy, which is theta old. All right? This is the key idea, the key intuition. If these are close, I can replace this distribution over states with the old distribution over states, and the approximation will be fine. It will be good enough. So how does this go? So we start with this expression here. Sorry, it's a bit cut off at the top, which is just what we've seen in the last few. And now let's do this decomposition, right? I'm going to do this decomposition into an expectation over actions and an expectation over states, right? So here I've done it for the case of a finite number of actions, but this whole argument generalizes to infinite, to continuous action spaces. Just replace this sum with an integral. So what I've done here is this expectation over actions, I've made it explicit. I've said, well, this expectation over actions is just going to be sum over all actions, the probability of taking that action under my new policy, weighted by the advantage for that state and that action, right? So all I'm doing here is I'm making the expectation over actions explicit in here, and now I'm only sampling my states according to my new policy. Anyone have questions about this? This is fairly straightforward. Great, fairly straightforward. All right, now we're going to do our approximation. So our approximation is to replace this distribution over states, right? This distribution over states that I visit, replace it from the state sampled according to my new policy with state sampled according to my old policy. That's the approximation. That's the approximation you make for deriving surrogate advantage. Okay, now what? So now I'm going to do this important sampling trick. So what's going on here? What's happening? So all I'm doing is I'm multiplying and dividing by, I'm multiplying by 1. So this term here, all I'm doing is inside the expectation over actions, so the sum over actions, I'm multiplying by the probability of the action under my old policy and dividing by the probability of the action under my old policy, right? So I'm getting this important sampling ratio here, this ratio of the probability of actions under the policy, and now my expectation is with respect to the old policy, my expectation over actions. Any questions about this? Yeah? Okay. And so, making this, so remember this move here at the top where we made the expectation over actions explicit. We can again just make that, sort of undo that making expectations over actions explicit. And so because this is now an expectation with respect to theta old, I can now generate trajectories according to theta old and then use this expression here. Right? Any questions about this? It's the last step. Okay, so fairly straightforward moves. And this thing that we're left with, so this is the relative policy performance. This is the relative policy performance identity. And we approximate that with this thing here, where now we are sampling trajectories according to theta old instead, and we have this important sampling ratio coming in here. And this thing here, we call this the surrogate advantage. So this beast here, this is the surrogate advantage. Any questions? Mm-hmm.
So it's not an approximation. This is
No, it is an approximation because, so the approximation comes in when I go from this step to this step, and it comes from the fact that I'm moving the distribution over states. So I'm approximating the distribution over states from my new policy with the distribution over states from my old policy. So that's where it's an approximation. Yeah.
Yeah. So what type of when you do that approximation, what type of like guarantees exist around this? Because it seems
Yeah.
to me that you wouldn't be able to. It doesn't sound like a smart idea, at least, to just keep doing this, right? In essence, kind of bootstrapping your trajectory, right?
Yeah. So
Can you overcome this maybe by just adding noise to your to this distribution?
So the question was, are there guarantees? And there are guarantees for surrogate advantage. So you can prove that. So I said at the start that when theta nu and when pi theta nu and pi theta alt are close, then I can make this approximation because the distributions will be close. And there's a sense in which there's a rigorous sense in which this is true. That if you bound the I think it's expected TV, so total variation distance, between these different policies, then you can also get a bound on how the error of the surrogate advantage and the policy difference here.
Okay, but is there a bound between those distributions?
Is there? So yeah, if you bound, I think it's the expected TV distance between these according to states sampled according to theta old. I think is the how the bound goes, if I remember correctly. So in other words, like you can't, if the two policies are close, you can't do arbitrarily badly. There's a limit to how badly you can do as they get closer and closer. And in the limit, as they become really, really close, this becomes a really good approximation, right? So yeah, there are theoretical guarantees for this approximation here. Great. Any other questions? Cool. Okay. Okay. So why is this useful? Why is this a useful thing to introduce and to use? So let's write out the surrogate advantage again. So trajectory sampled according to my old policy, sum over the time steps on the trajectories, probability ratio, advantage function. So I only require data sampled according to my old policy, right? So I do a bunch of rollouts in my environment according to my old policy. This gives me my data for that old policy. And then I don't need to sample any new data for computing this, right? So I don't need to already know in advance what my parameters are going to be, which I did need for the previous expression, right? So I only require data sampled according to old policy. And we know how to compute these advantage estimates, right? We learned last week, for my old policy, we learned how to compute advantage estimates for each state action pair for that old policy, all right? So that's also good. That's also fine. And then this thing, so all we need to do is be able to compute the probability of any given action under my new policy. And this is easy. Like we saw how to do it at the start. Either you're just like getting network, you're getting the logits from a network, or you're getting distribution parameters. But yeah, this is also fine. So everything now is fine. I don't need to know in advance what theta nu is going to be. I know how to compute these. I know how to sample that, and I can readily evaluate the probabilities of actions, right? So this is why the surrogate advantage is useful. Any questions? Yeah.
Still slightly confused about, like, we said we don't need to know theta nu, but we do need to know it to get the sample the action.
Yeah. So the question was, I said that we don't need to know theta nu in advance, and what I'm saying is that evaluating probabilities for a new set of parameters is in some sense easy, whereas doing rollouts for a new set of parameters is very, very hard. So the sense in which so the reason the previous one was problematic is because I needed to be able to do arbitrary rollouts for any new policy. Here, all I need to do is evaluate probabilities for any new policy, and that's very easy to do. Yeah. Anything else? Yeah?
So could you do multiple updates before you update one?
So the question was, could you do multiple updates before you update theta old? And the answer is that's exactly what you do, yes. So this is why this is so useful, because provided these policies are close to one another, I can do many updates of theta new without updating theta old. So I do many gradient steps to update theta new, and then I've got my updated value of theta new, and now I make theta new, theta old, do a rollout, and then do multiple gradient steps again. Okay? Yep.
If we are trying to keep the two probability distributions as close as possible, wouldn't convergence be really slow?
Not necessarily. So the question was, if we're trying to keep the two distributions very close, wouldn't this mean that convergence ends up being slow? And the answer is, in a mathematical sense, yes. In a practical sense, no. So in the mathematical sense, I said that there's a bound you can get on the surrogate advantage that tells you that it's a good approximation, provided the policies are close. In practice, this bound ends up being excruciatingly severe. You basically can't really move your policy that much at all in order to satisfy this bound. So what we do is we just go, well, provided they're pretty close, it's probably going to be okay, and this works just fine in practice. So in practice, we don't actually keep these super close to one another, not nearly as close as would be necessary for the theoretical guarantees to come into play, but it still works fine. Yeah.
You can do right without applying many gradient directions, just take note of many modifications that are needed between old and new without actually applying.
Yeah. So the question was, could you just take note of what directions you need to go in without actually applying them? I guess that would be another way of going about it. But so let's sort of press forward. A lot of ideas have come up of how you do this, and you're already sort of preempting a lot of how PPO works and problems with other methods. So the surrogate advantage, we can approximate this by we're going to replace the expectation with a sum over sample trajectories. So this is just the same Monte Carlo trick that we used in the previous one. We have an expectation. This is we can't compute this, so instead we sample a bunch and then we compute the empirical average instead. And we're going to replace the advantage function with advantage estimates, which again is fine. We learned how to compute advantage estimates last week. So how does this work? So this is the surrogate advantage. This is an analytic expression. It lives in the world of maths. And this is what we approximate it with. So we're replacing the expectation over trajectories with an empirical average over a data set of trajectories generated by rolling out my old policy. And we're replacing the advantage function here with advantage estimates of advantages of actions according to my old policy again. So these advantage estimates are advantage estimates for the old policy. So this expression here, this lives in engineering world, right? This is a thing that we can actually compute and use. All right, everyone comfortable with this? Or I'll also press on, it's not too tricky. Nice, okay. So now let's talk about optimizing the surrogate advantage, which is what we want to do because optimizing surrogate advantage will hopefully lead to an increase in the policy objective, which is the thing that we care about. So here's the key idea. We have a surrogate advantage. Let's just optimize it. And by optimize, we mean gradient steps, because that's the only way that we know how to optimize things. So I'm going to use my current policy to sample a data set of trajectories. The data set D of trajectories, just roll that policy out in the environment. Then for each state action pair that occur along each one of those trajectories, I'm going to compute an advantage estimate. We learned how to do this next week. You can do it in a variety of ways. You can do it in a TD way. You can use generalized advantage estimation. You can use return minus value. Loads of ways of computing advantage estimates. Pick your favorite. Use that to compute advantage estimates. Then we're going to perform multiple steps of mini-batch gradient ascent on the sampled surrogate advantage, right? So this beast here that we met on the last slide. We're going to do multiple update steps with respect to theta nu. So multiple gradient steps with respect to theta nu of this thing here. The theta old is held fixed, and theta nu is the thing that I'm going to update, right? And then we're going to fit any value functions we're going to use using multiple steps of mini-batch gradient gradient descent on typically an MSD objective, and you're going to form regression targets using bootstrapping. We met all this stuff the previous lectures. Great. Any questions about this? Okay. So this is like just an algorithm one could write down that optimizes the surrogate advantage. And then you loop this, so theta new becomes theta old. You do another set of rollouts, and you proceed downwards as follows. Just keep looping this. Okay, so what goes wrong when you do this? So does anyone hazard a guess before I tell you why this algorithm doesn't work in practice, or is a bad idea?
Maybe the value function no longer match.
Yeah, so the suggestion was maybe the value functions don't match. Luckily, because you're doing this value update step here, it's actually going to be fine. You are correct that what I really want to do is probably interchange this value function update step with the policy update step, so do these in the reverse order. Because if I do that, then my value function will represent values with respect to my current policy, and then my advantage estimates will be better. So yeah, it would actually probably be better to interchange these two steps for this particular algorithm. Yeah. Other suggestions for what goes wrong when I try to do this, or what could go wrong? What are potential failure modes for this?
Does this converge?
Because it seems like it's incentivized to just pick very different actions.
So the question was does it converge? Because it seems like it's incentivized to pick different actions. So let's talk a little bit about the incentivization here. So let's take another look at this. Okay, so how do we maximize this thing? So remember, I'm taking gradient steps to increase this thing. How would you maximize it? What is the optimal way to maximize this objective here?
Increasing the probabilities, positive advantages, and decreasing the probabilities of negative.
Yeah, so if I keep optimizing this, and I just do that, until I converge, what will I do? Well, for any positive advantage action, so any time that a hat t is positive, I'm going to just send this to 1, right? Or in the case of a continuous action space, as high a density as I possibly can on that action, right? But in the case of discrete, I'm just going to send this to 1, right? What about negative advantage actions? Well, if an advantage is negative, then the optimal solution is to set this to 0, right? And so if I keep optimizing this, what I expect is that my policy essentially, for any positive advantage action, just immediately sets that to always do that action. If any negative advantage action, sets it to never do that action, right? If multiple actions are sampled off the same state, you have some competitiveness where you expect that the action that has the highest advantage is the one that you fixate to. But yeah, the basic problem here is that if I optimize this, then I just end up setting all positive advantage actions to 1, all negative advantage actions to 0. Yeah. Okay, why is this a bad thing? Why is this a problem? Well, the surrogate advantage, if you just optimize it directly, then you get to extreme policies. And these extreme policies will be very far away in general from your previous policy, right? Compared to your previous policy, they're going to be very different. They're going to be very far away. And why is this a problem? So why do we care about them being far away?
Because then the approximation no longer really holds.
Yeah, because then the approximation doesn't hold anymore, right? So the optimizing the surrogate advantage only makes sense when they're close, but if I just optimize it forever, then I'm going to get something that's far away and it's not a good approximation anymore, right? And so the surrogate advantage only approximates policy improvement when the policies are close, and that if you end up with policies that are far apart, then optimizing the surrogate advantage can actually decrease this thing, right? So you actually end up doing worse. And that's what you would see in practice. If you just keep optimizing this, you'll get rapid collapse of the policy and you would end up doing worse overall. Okay, so any question about this before we cover what's the solution? How do you fix this problem? Okay, so we'll understand why it's an issue to optimize just directly the surrogate advantage. And so now we're going to introduce PPO clip, which is the version of PPO that is preferred and used more in practice. And we're going to see how it solves this problem. So the idea, the sort of trick that PPO clip employs is called probability ratio clipping. Let's have another look at the sampled surrogate advantage, the empirical surrogate advantage. And let's separate out positive and negative advantage actions. So we saw before that we care about these different cases. If an advantage is positive, we expect this to be increased to 1. If it's negative, we expect it to be decreased down to 0. And all I'm doing here is I'm taking this thing and I'm just going to rewrite it as the sum over positive advantage actions and the sum over negative advantage actions, right? Everyone happy with this? Any questions? Okay. Great. And let's first start with this positive advantage term. So this is my positive advantage term. And the key idea is that I'm going to remove the incentive to increase the probability by like arbitrarily large amounts. So I only want to increase the probability by a relatively small amount. So I'm going to stop increasing the objective when the new probability of an action exceeds 1 plus epsilon the old probability of the action. So epsilon here would be something like 0.2. This is like a fairly typical number to see, 0.1. These are, in the grand scheme of things, quite large numbers. And this is where like I mentioned earlier that like in practice, the guarantees don't like actually hold, but it doesn't matter. And epsilon being 0.2, the guarantees definitely don't hold, but it doesn't matter because it works well in practice. So we're going to stop increasing the objective when the new probability exceeds the old one by 1 plus epsilon times that old probability. So we'll replace the positive advantage term in the objective with this thing here. So the minimum of this and 1 plus epsilon times the advantage. All right? So what I'm doing here is that when this probability exceeds 1 plus epsilon, this thing doesn't go up anymore. Right? It's capped. It's capped at 1 plus epsilon. Any questions?
Sorry, when does this, over what horizon does this cap hold? Is this for a single update? Is this for the entire training run? Like,
yeah, so over what horizon does this cap hold? And so every time I do a new set of rollouts, I'm going to compute my surrogate advantages again. Okay. And I'm going to, again, be just applying this clipping trick.
So every time you update,
yeah, every time you update the parameters, you after a collection of gradient steps, then I update theta and I get new ratios.
So conceptually, this still doesn't like fully like bound the total change in pi. So how is this different than just like using a really tiny learning rate?
Right. So the question was, this doesn't bound the change in pi, and so it doesn't stop pi from getting very large, but it does remove the incentive for the action probabilities to change by a large amount, right? Because if I increase the new probability by more than 1 plus epsilon times the old one, if I set it slightly above, then this objective isn't going up anymore, right? And theta old here, remember, this is according to data sampled according to theta old. Okay, so I'm just going to move this advantage inside. The advantage is positive, so I'm just going to move this inside here. Okay, now let's look at the negative terms. So these are the terms where the advantage is negative. And now we want to stop the probability getting too low. So what we're going to do is we're going to stop increasing the objective when the new probability is smaller than 1 minus epsilon of the times the probability under the old policy, right? So again, we're going to clip and stop the surrogate advantage going any more positive when we decrease the probability by this amount. So we'll replace the term in the objective with this thing here. So now it's the max of these probabilities and 1 minus epsilon, right? Because I care about when it's smaller. Right? Okay. The advantage is negative, so I'm going to move it inside. When I move it inside, I have to replace this max with a min. So I have this beast here, right? Everyone happy with this? Any questions?
Is epsilon always modified to the lifetime of the optimization?
Is epsilon modified through the lifetime of the optimization? It's typically not, I don't think, changed or modified within like a batch of updates, but is across the entire thing, right?
Increasing.
Yes, typically you would increase your epsilon.
This is an argument in favor of the idea that it's a different way of introducing learning, like increasing in nature for the optimization.
Yeah, you typically would also decrease learning rate, I think. Yeah. Cool. Okay. So we have our total surrogate advantage decomposed into the positive and negative terms. And then we're just going to do our transformations. So remember, what these transformations are doing are they're removing the incentive for probabilities to get too high or too low. And that gets us this. All right? And then we can just write that as this thing here. So we have minimum of, so now we're combining these two terms together. I've introduced this g epsilon a hat here. And this g epsilon a hat is just 1 plus epsilon a hat if a hat is positive, and 1 minus epsilon a hat if a hat is negative, right? So I'm just combining these two terms here and differentiating according to whether the sign of the advantage is positive or negative, right? Nothing fancy. Any questions? Great. Okay, and this is the PPO clip objective, right? So this thing here, this is called the PPO clip objective, and this is the thing that I'm going to do many gradient ascent steps on with respect to theta nu. So brief aside, why do we call it PPO clip? It's not entirely clear what's being clipped here. We're taking a minimum, but there's another sense in which it's like, or there's a different representation of this under which it's more clear why we call it PPO clip. So this is the PPO clip objective. This is maybe the easier one to understand conceptually, but you can also express this like so, where you have the minimum of the probability ratio times the advantage and the clipped probability ratio times the advantage, where the clipped probability ratio is the probability ratio clipped between 1 plus epsilon, 1 minus epsilon, right? So you take this probability ratio, when it gets above 1 plus epsilon, you clip down to 1 plus epsilon, and when it goes below 1 minus epsilon, you clip back up to 1 minus epsilon. These two things are equivalent, not going to run through the derivation. This form is, I think, slightly easier to understand, and this form is where the name PPO clip comes from. Right? Yeah, so the probability ratio is clipped between 1 minus epsilon and 1 plus epsilon. Okay, now the PPO clip algorithm, like written out in full. So start with an interaction step. I use my current policy to sample a data set of trajectories. Right, so I do a bunch of rollouts, maybe 10 rollouts in the environment. I've got my data set of trajectories. Then I do my policy update step. For each state action pair, I compute an advantage estimate. And then I perform multiple mini batch gradient ascent steps on the PPO clip objective, which is this thing here. Right? So I'm doing multiple steps with respect to theta nu on this objective here that we've met so far. And then I update my value functions in the appropriate way. Implementations differ in terms of the order of these two steps, policy update and value function update. The argument for doing value function update first is that your value functions will be more appropriate for the policy that's being pursued, and this means that your advantage estimates will be more accurate. The argument to doing it after is that you don't want to overfit to the data that you have, and provided your policies don't change by a whole lot, this shouldn't be a major problem. I don't know which one ends up being better. Implementations differ on which they do first and which they do second. And then you loop. So you set theta new into theta old, you go back, you generate trajectories, multiple mini batch gradient ascent steps, update value functions, come back, right? This is PPO. Okay, why is PPO better than A2C? Why is it more popular and used more often? So they're very similar. They both form advantage estimates. They both they both do rollouts, generate data sets, then discard it. what do they differ in? They differ in how they update their policy. In A2C, you perform one gradient step on the following objective, right, which is the sum of the advantages log probability of the new actions. PPO clip performs multiple, typically mini-batch gradient steps on this objective. So we can see that why PPO clip is better is because it's more sample efficient, because you can do multiple update steps of your policy for each set of data that you get, right? So both of them generate a set of data, and PPO clip uses that data more aggressively than A2C. It uses it to do multiple policy update steps, as opposed to A2C, which just does a single policy update step, so a single gradient step on this objective.
You could make A2C do the same thing, right?
You can make A2C do the same thing, but this tends to become unstable after a few steps, right? So you can like just to hack together an algorithm where you do A2C, but you do multiple gradient steps on theta nu, but this doesn't tend to work after a certain number of steps. Whereas PPO clip is like pretty safe to optimize this quite a lot. So to do multiple steps before you go, oh, okay, like it's not a good idea to do this anymore.
Because for A2C clip.
Yeah, but I think A2C clip just ends up being PPO clip. Yeah, so there's a lot of similarities here, right? There's advantages. You can kind of see how you're taking the gradient of this with respect to theta nu. So you're going to get a grad pi nu over pi old. But if you take the gradient of this with respect to theta nu, you get grad pi nu over pi nu. I think this grad pi nu over pi nu rather than pi old is the thing that maybe means that this doesn't work as well. So it's this probability ratio that becomes the important thing. Okay, let's summarize the algorithm and close out. So first of all, it's model free. What does this mean? It learns directly from experiences sampled from the environment. So we do a batch of rollouts. This generates our data set, and this is it. This is we don't need to build a model. We don't need to be given a model. It's on policy for the same reason. So you do a bunch of rollouts. You gather your data set. You do many value function update steps. I should say many policy update steps. You do many policy update steps, many value function update steps, and then you discard it. So you're on policy, you don't use a memory replay buffer. It's actor-critic because you learn a policy and typically a value function to form advantage estimates. So you need your value function to form an advantage estimate of some kind. And it can be applied to any state and any action space. So we discussed at the start how you would make your policy for discrete action spaces and for continuous action spaces. And you can apply PPO clip to either of these action spaces. Thank you all very much.